All right. So next we'll have Pablo Moreno Munoz presenting heterogeneous multi-output Gaussian process prediction.
Thank you. Well, this is joint work with Antonio Artés and Mauricio Álvarez. The problem that we deal with is when we observe pairs of input-output values where the inputs come from the real domain, but the outputs are a mix of continuous binary, categorical, or discrete variables. This is what we know as the heterogeneous problem that is also a combination of different statistical data types. We want to jointly modeling this with Gaussian processes, but what we know is the majority of approaches for multiple outputs focus only on all regression or all classification tasks. That's the reason why we provide a novel extension of Gaussian processes for accepting any arbitrary combination of heterogeneous data. We find interesting applications such as the medical scenario where we can have a patient being monitored by several physiological metrics such as heart rate or glucose level, each one belonging to a different nature. Also spatiotemporal analysis and even Bayesian optimization with multiple outputs. I begin by defining the heterogeneous likelihood in our model that we assume is a product of the different likelihoods, each one belonging to a different statistical data type. Each likelihood has its own parameters, and in the Gaussian process literature, this is usually assumed to be a nonlinear mapping of a function f that comes from a GP prior. For example, this function will be the sigmoid for the Bernoulli in binary classification, the exponential in the Poisson case, and the identity function for the mean parameter in the normal distribution. The question is, how do we jointly model these functions f? Well, what we assume is that all of them are a linear combination of a smaller set of latent functions u of q. Each one belongs to a different or independent GP prior, and implicitly what we are doing is imposing a multi-output GP prior with a coregionalization model of covariant matrix. We make all of this scalable by applying sparse approximations and variational inference. And our lower bound has interesting properties such as divergence that factorizes over the Q latent functions and also the expectation that factorizes across samples. And of course, this is amenable for stochastic optimization. We use the variational version of the EM algorithm to fit both variational parameters and hyperparameters. Our results show improvements in multitask learning where we are able of predicting in a binary classification task using information from a Gaussian regression 1. And of course, this is better than independent learning, and we demonstrate it in our experiments. Our model is also applied to large-scale datasets such as the London house price data, where we combine binary classification and heteroscedastic Gaussian regression. What we saw is in that in the posterior curves, both tags share modes. Our code is publicly available on GitHub, and we present an easy syntax for defining any arbitrary combination of heterogeneous likelihoods. If you are interested, come to our poster, please. Thank you very much.